I'm really curious about those overpasses that seem to be floating in the sky. How exactly are they built? Today, let's explore the construction of the tallest viaduct in France, the Millau Viaduct. The Millau Viaduct reaches a staggering height of 343 meters, which is actually 43 meters taller than the Eiffel Tower. It spans a total length of 2.5 kilometers, yet is supported by only 7 piers. The completion of this bridge can truly be called an engineering marvel. It's located in the Tarn Valley in southern France, a place known for unpredictable weather and strong winds. Wind speeds of up to 200 kilometers per hour are quite common here. On top of that, the geological conditions are complex. Building a stable foundation capable of supporting such tall piers and a massive bridge was a serious challenge. After conducting a thorough geological survey, engineers began laying the foundations at designated locations. To ensure the foundation's stability, they had to find solid bedrock that could bear the immense weight. They had to dig down 15 meters before finally reaching it. To ensure a stronger connection with the bedrock, the engineers drilled holes into it, inserted steel pipes and rebar structures, and then poured concrete. This created 4 piers fully bonded with the bedrock. With this as a base, they could then begin building the foundation. First, they placed a 4-meter-tall prefabricated frame, then constructed a dense steel rebar mesh inside the frame. After pouring the concrete, they waited 1 to 2 days for it to cure. Then raised the frame, added more steel reinforcement, and poured concrete again. This process was repeated again and again until the entire foundation was complete. Once the foundation was finished, the next step was building the main piers. This stage used a self-climbing framework to construct the steel reinforcement and pour concrete layer by layer. As the piers grew taller, engineers installed tower cranes on them to lift workers, equipment, and concrete materials to the top. When the construction reached 2/3 of the total height, the piers were split into 2 parts. This design had 2 main advantages. First, it reduced the impact of strong winds on the piers. Second, it helped evenly distribute the load. During the construction of these several hundred-meter-high piers, to ensure they remained perfectly vertical, engineers used millimeter-precision GPS positioning equipment. Thanks to this, the final positioning deviation of the piers was only 2 to 3 millimeters. At last, all 7 piers of varying heights were completed. But the real challenge was just beginning. The distance between each pier was 350 meters. Concrete blocks couldn't support such a large span. So, engineers decided to use steel bridge segments instead. However, if they prefabricated such long bridge sections on the ground, they would weigh tens of thousands of tons. There wasn't a crane big enough to lift them. And even if there were, it could break the piers from the weight. Eventually, the engineers came up with a solution. They chose to weld the steel bridge segments one by one along the side of the bridge alignment, and then use a hydraulic system to slowly push the bridge forward, bit by bit, until the final connection was complete. To prevent the modules from collapsing over such long spans, they built temporary support structures between the piers and installed sliding mechanisms on top of the bridge towers. Even with all of that, the bridge was so heavy that the lateral friction force on the piers was too great, which could also cause them to topple and lead to disastrous results. So finally, the engineers decided to install hydraulic shifting devices on all the piers. Each device worked in coordination to push the bridge deck forward. This is how the system operated. But because the spans between piers were so long, to ensure the bridge's stability, they also installed steel tower caps and steel cables atop the piers. The tower caps were 90 meters tall, and the steel cables weighed 700 tons. But compared to everything else, this part was relatively easy. In the end, the bridge was connected piece by piece. The connection deviation was only 1 centimeter. A total of 36,000 tons of steel were used in the entire bridge. The Millau Viaduct overcame massive challenges, height, geology, and more. Its majestic structure and cutting-edge design have made it a benchmark in global bridge engineering. Still, compared to our infrastructure-obsessed nation, it's just a little brother.